So, good morning, everybody in the room and online. My name is Wolfgang Peters from AVT. I'm the managing director, and I will explain today on two examples how we installed DAB at two customer sites. Yeah, we have a few overlapping things. What Lars Peter already told you about redundancy, but I will do it shortly. A few words about our company. This one is always a challenge here. Yeah, this one. So the most important thing is we celebrate our 30 years birthday this year. So and in this 30 years, of course, DAB was a very important part for our company, which you see in the next slide. We are also working on three different areas. One is DAB, of course. The other one is telephone hybrid systems. We are one of the world telephone hybrid talk show system supplier. And we do also classical audio codec transmission for transmitter to for studios to transmitter locations or from events to radio stations. Yeah. So you see, that's our commitment to DAB. We did a lot of things. We started in 1997 with together with Fraunhofer Gesellschaft, at that time also with German Telekom and Roland Schwarz, developed the first multiplexer and the first service multiplexer that was a big box with a lot of signal processing inside. Today, as Lars Peter already explained, it was really evolution today. You will see later than in the pictures what happens. And since 1997, we developed multiple products, monitoring decoder, then different kind of DAB encoders. We have then developed the redundancy switch at that time. At that time, and was in 2011 exactly. That was a separate box, but today we do everything in one box. Yeah. And then we started in 2018 and the own development of a DAB multiplexer. First thing was the DABMUX Go, is a very small multiplexer for small scale broadcasters. And then 1 year later, we offered then the DABMUX Plus, our professional platform, to handle all the bigger broadcaster requirements. 2023, we developed the new monitoring decoder, which can handle up to 20 ADI inputs to monitor at the same time. And last year was, of course, everything was focused on ASA, the emergency warning system in DAB. And this year we start our new multiplexer platform, also something with microservices. But you will see that on IBC, what we provide then. So what is important for a reliable DAB multiplexer headend? It is a matter, of course, for the most of you who already installed a DAB system. Of course, you should have a redundant multiplexer system. If it's not redundant, you can forget it for a really real used network, because there are so many possibilities that a multiplexer can fail, not because of the hardware fails or the virtual server fails, because of something in between. The most problems we have in the network. And therefore, the two-way transmission is also very important. It makes no sense if you have a complete redundant headend, but only one way to your transmitters. Therefore, think always about a two-way transmission to the transmitter sides. If your E1 network or your IP network fails and you have nothing, at least an internet connection to your transmitters, then you lose everything at the end. And therefore, we recommend also to use reliable networks. Internet is really the last selection you should do. Use MPLS lines or E1 networks is very often used. I was really surprised how often users have E1 networks, but it is as it is. But they will change. So all the users will change in the next 2-3 years to IP, and that's a good thing. Nice to have, of course, redundant DAB encoders, but that's a matter of money. If you want to spend a second encoder or not. Sometimes people want to use web streams. I'm really not a fan of this approach, because web streams, you have a long delay in web streams, 30 seconds. So if you have a switch then from a normal program, from a DAB program to web stream, then you have immediately a gap of 30 seconds. Also, the transmission of metadata is more a problem. And that is not really. And if you use an AC web stream with 96 kilobit or something, and then re-encode in DAB+, it's not a good idea. It sounds really weird. Yeah, don't do that. Yeah. And then the other thing is, of course, if you have independent sites, the best way. So a lot of customers do that in City 1, and the other headend is then installed on City 2. Nothing can happen. Yeah. Or at least that you have two different buildings or two rooms. Yeah. So that is the strategy to make it really reliable. Yeah. In case of remote DAB encoders, if the encoders are installed in the studio, that's very often used in Europe. Then, of course, the IP network between the encoder side and the multiplexer side has also to be reliable. Yeah, you should have also an independent internet connection at least as a second line. Yeah, used for the main main encoder and reliable MPLS line or whatever you have, or an SRT transmission between. But for the second one, an internet connection at least should be available. Yeah. Yeah, and then of course we have different kind of possibilities to make the transmission secure. Typical thing is our secure streaming. 2WCOM offers it as dual streaming, if I'm right, yeah. And all the manufacturers have something like that. And yeah, as well as Gates Air, of course. Sorry. Yeah, so there are a lot of features inside the encoders to make it more stable, yeah, more reliable. Yeah, and you should do everything what you can do to make it as best as possible. Yeah. And why is redundancy important? Yeah, an availability of 99% means 53 minutes per year. So if you have an important advertisement customer and he loses the advertisement, then you will get really stressed. Yeah, and I can't imagine that a lot of providers have 99% availability. 1997 is, I think, is typical. Yeah, so you have then 3 hours or whatever per year. Yeah, and the typical downtime is, of course, power failure, error in contribution or distribution network, and of course a simple software update. Yeah, if you want to do that, it needs a few minutes. Yeah, and you don't want to have always an interrupt if you have a system update. Therefore, it's important to have a redundant system. And to be clear, if the multiplexer fails, you lose everything. Yeah, all the programs in this multiplex. Yeah, that's not always clear to customers. If we discuss it, they think, yeah, there's an encoder and we can transmit it in any case in any way to this one, but it doesn't work. Yeah, so if you have no redundant multiplex, then it fails completely. Yeah. So that we speak about all of the same things, so that we have the same wording. Here, a principal structure of a DAB headend. We have on the left side the contribution network. And the contribution network consists of multiple service providers. Yeah, as Lars had in his slide, the same is the service provider 1, service provider 2. Then we have a service provider N with multiple programs, for example. They transmit their programs then via an MPLS or internet network to the multiplexer side. Yeah, important. This transmission protocol is not standardized. Yeah, you see, we have here different kind of possibilities. We have the EDI STI standard. Yeah, it's but it was not really mentioned for that purpose. Then Fraunhofer has the MUX-ENG protocol. We have the AVT MUX protocol. I'm not sure what's your name is in your protocol, Lars, but you have different kind of things. That means you cannot combine systems from different manufacturers, or you lose, let us think, comfort in the system. Yeah, that's important to know. Yeah, and on the multiplexer side, in the middle, the ensemble provider, they run the complete headend. Yeah, the multiplexer headend, but there can be also a local service provider. That's, for example, a big public broadcaster, which can run here multiple encoders on directly on the ensemble provider side. And we have very often also in Germany data service providers, which offers then the TPEG signal or the SPI, the EPG information and so on a dedicated service. Yeah, so that's the part which you have available. On the distribution network, we have the EDI standard. That's really a standard. you can be very sure that it works with all the systems, with all the transmitters. We found not that much problems, but you can explain maybe more. And as I said, the transmission and the distribution network runs via MPLS or E1 lines, yeah, or satellite and something in between. Yeah, so that will helpful. Important to know, the system is typically completely synchronized to GPS. Yeah, so also the anti-peak clock, which we need for synchronizing everything, must be GPS derived. That's important. Yeah, and if you're using I67 in the audio contribution, then of course the PTP V2 clock, which you have in use there, is also necessary that it's GPS derived. Otherwise, you will have problems in your network. Yeah. Yeah, that's now a redundant DAB headend on the service provider side. As I said, it's a matter of money, of course, if you spend redundant encoders. Of course, if you want to be sure there's no other way to have redundant encoders, then we transmit the signal. Here in this example, one main program runs via the MPLS line and the second backup encoder via the internet, and is fed then the ensemble multiplexer main and the ensemble multiplexer backup. So important is both multiplexers have both programs at the same time, always available. So if something happens here, yeah, it takes over automatically, seamlessly. Yeah. In our product, the audio is also synced, so you cannot hear that if you remove one encoder, it works as it is. Yeah. Okay, and if you have only one multiplexer, then you see we have here the ADI-A signal transmitted to the transmitter sides. But if you have a backup multiplexer, then we have here a changeover. We exchange the frames between the two multiplexers. And in this case, then we have a two-way transmission. Here you see the two outputs, which we transmit then to the transmitter sides. And that example I have here, MPLS main and a satellite backup connection. Of course, very often it's a mix. Yeah, you have maybe transmitter sites which are really very special locations, areas where you cannot reach it via an IP connection, for example. Then of course customers do that via satellite signals. Yeah. So what happens if the input fails, network switch error or something like that? Then of course the system switch automatically to the backup multiplexer, and you see all transmitters receive then the redundant signal from the multiplexer B. Yeah. So if the multiplexer A has no longer input, then you can't change something. But again, we exchange between backup multiplexer and main multiplexer, so the same what Lars Peter explained before. We exchange the frames between both systems, and then you have still a running seamless switching to the transmitter sides. Yeah. If we have a second failure, if we have here an output error on the multiplexer B, then of course we lose the second way. But although the multiplexer A has no input signal, he gets the changeover signal from the B multiplexer, and then we have still a working system, yeah, without any interrupt or something. Yeah, but in this case, you should do something. You should work on your network. That's clear. Yeah. Yeah, I think we saw that already from Lars Peter, the redundancy switching in detail, but it's very often a question how it works. You have to understand that a multiplexer consists of two different or multiple units. Yeah, we have the encoder part maybe in the multiplexer. We have the multiplexing part in the multiplexer, and now we have also the redundancy switching part in the multiplexer. Yeah, it's all in one box today. Yeah, and as Lars already explained, if you shift then the both signals from multiplexer A and B, then we can monitor on the redundant switch. So we are here on the left side, you see the small redundancy switch. On the top, you see the two frames from the two different multiplexer outputs. And on the redundancy switch, we see then the output signal, which you see in the last, in the bottom frame line. Yeah, and if one frame fails, we can simply take over the frame from the other multiplexer. Yeah, so it's more or less the same what you heard before. Yeah, good. Yeah, case studies. Now we come to the both DAB implementations we did. One was NDR in Germany. Yeah, that was at that time really a challenge. This project, and the other one is Polish Radio and Emitel in Poland. Yeah, let's start with NDR. So the requirements was they want to have 17 fully redundant encoder and multiplexers. In the beginning it was 16, but they extended it 2024 to 17th multiplexer head end. And the challenge was really they asked for a full flexible system, and each multiplex should be completely independent. That means in audio bitrate and protection level, with slideshow, with signalization, all should be completely independent. Yeah. And we asked often to NDR, is it really true what you want? Because if you calculate, we calculated all the programs. At the end, we had 2 times 139 programs to a total 278 encoders in that system. That was really a lot at that time. Yeah. And the other thing was for each channel, for each audio channel, they asked for a separate PAD inserter. So say a separate PAD channel that for dynamic label as well as for slideshow. Yeah, that was really a challenge. Yeah, and of course each multiplexer has its own NPAD channel, TPAC and SPI. Then also the DAB and DAB FM linkage was a requirement. Yeah, and traffic announcements, of course, they use very often. And then they made also a scheduler running for dynamic reconfiguration. And that the reason for that was their traffic center where they do the announcements, it's not completely occupied the whole night. And you cannot send a traffic signaling on the network if you do not traffic announcements. That's not allowed. Therefore, they switch off in the night the signaling of the traffic announcements. That was the reason for the scheduling. Yeah. Yeah, and then we had the parallel ETI and ADI distribution because they have a few special extra located transmitter sites, which was only available via satellite. And but they used and today they use still the ETI network for the most transmitter sites. And at that time there was also a request for a commercial broadcaster because there was in the beginning a mix of a public broadcaster and a commercial broadcaster. Yeah. But they stopped that already because the commercial broadcasters have now their own multiplex in that area. Yeah, yeah, and that's the block diagram. We have here on the left side the audio and data playout. You see we have a lot of different companies behind. So the audio signal comes from a Lavo router via MADI. That was the source of the different audio programs. So in total, 2 times 139 programs. Then they use the 4=1 as a company name. It's a small company in Hamburg. They offer the Maongo slideshow server, but this server is able to play out all these different slides. And they use, for that case, our API, which is a simple thing for them than to send the picture. And it's very nice. So they optimize the pictures in the size so that is, and they calculate always how long it takes to transmit the pictures, because we do always 10%. We can override it, but typically we use 10% of our bitrate is a good value for transmission of PAD. And then you can calculate exactly when you have to play it out so that is in sync with the audio title, because the playout system can that manage. Yeah. Then we have the so-called TIC server from the company is called GEWI. They provide the dynamic label plus signals, the TPAC signal, and the traffic announcement signal, which is transmitted in our system via UECP to the multiplexer system, and the TPAC comes via FTP simply. Yeah. And the SPI is realized from RBB in Berlin. Yeah, they do that for all public broadcasters in Germany and send the stream via their corporate network to the multiplexers. And the DIRA radio playout is from CGI. They are responsible for the service linking, what I said. So they have hard and software linking in their network, and that comes directly via the API to our system, yeah, from the playout system. In the middle, we have no MADI input into our encoders, but we have I67, and therefore we use the direct out Prodigy system, which converts the MADI signal into I67. Yeah, and each system can handle 256 channels, and you see we have a little bit more space for extensions, if you like. Also important, you see here the clock master at the Lavo core is a GPS master clock, of course. And this clock is also transmitted via the MADI interface, and the direct out converts this clock then into PTP V2 for the clock of the multiplexer. Yeah? So the complete system clock was then PTP V2. Of course, the NTP is still necessary for timing information, of course. Yeah. Yeah, and all these things comes then into the multiplexer. We have the redundancy switch, the solving multiplexer, the encoders, the PAD, NPAD, monitoring all in one box, and that 17 times. And you see, we did everything in redundant. Also, the audio data playout, it's really a redundant system. They have a redundant audio router, they have a redundant slideshow server, and so on. Yeah, so it's completely a redundant system. Yeah. Yeah, and on the output side, you see we have, as I explained, we have here the E1 network at the output side. A few transmitters are connected to the satellite uplink. It's in Ismaning, the Bavarian Broadcasting Corporation is doing that, yeah, for them. So they transmit via ADI the signal to Ismaning. Ismaning transported then via satellite to the different transmitters, yeah. And today they do the test to switch over everything to ADI. Yeah, that happens at the moment. Yeah, they do a few tests, and yeah, and I expect that the latest in the next year switch over to completely ADI. Yeah, you see now here a few pictures. That's the setup on the left side. Yeah, the 16 multiplexers here, and that's the user interface on the system. Yeah, you see here the different systems. Oh, that was the wrong one. Can you put on the second? Yeah. Yeah, that's the user interface here, the redundancy monitor. You see in a clear way all these 17 multiplexers here, and you can force to a system if you want to maintain something, yeah, if you want to do a software update or something like that. But you see immediately which system is currently on air or not. Yeah, so that's the user interface. I go back. Next one, please. Yeah, third multiplexer dashboard. That's the multiplexer dashboard where you can see all the information. You see the audio level, of course. Maybe you can also see here on the left side the small slideshow which is displayed here. The dynamic label is mentioned here. And here on the left side, you see also the RT, which means road traffic flash. So that this program is a road traffic flash program. We have also the hard and software linkage set numbers below. So if something happens, if something comes from the a radio playout system, then you will see immediately which linkage set is currently in use. Yeah, so that you have an idea what is possible. And the last picture, please. Go back. This one, yeah. Yeah, the NDR plays their own monitoring system, which all the information you see, that runs via Amber Plus. So we have also the Amber Plus integration in the system with all the information, and they build this nice web interface to monitor their systems. Yeah. Okay, then I go again. So, case 2, Polish radio Emitel. A little bit different. We have a redundant national DAB pre-multiplex system with 10 programs, yeah, and plus one backup encoder. Yeah, so they do not spend all encoders as redundant encoders. We have also here 17 regional multiplexes, and each multiplex contains the national multiplex plus 2 regional programs. Yeah, in total we have here then 44 programs. They won't spend not so much money for redundancy, and therefore they ask for N+1 multiplex redundancy. And for the regional head ends, that is typically not seamless because you have only one multiplexer and you have to decide which one is. There's also a priority, and you cannot do that with seamless switching. That's simply not possible with N+1. And of course, the same data service as NDR, SPI, but they used only here the logo. Then traffic announcement, TPAC, DLS, and SLS was also required. And we have here a parallel ATI, again, ATI, and the ADI two-way distribution. Special requirement at that time, it happens in 2020, was a nationwide crisis announcement. Yeah, ASA was not a point at that time, and we have implemented then our solution, which comes from the tunnel break-in systems, very similar to that. Yeah, yeah, and that is the block diagram of this network. We have here on the left side an audio router, which manages then the N+1 DAB encoder audio input. It's not a perfect solution, I think, but what can we do if they do not spend money for the redundant encoders? Yeah, but at the end, at least they have a kind of redundancy. Yeah, then at least they have 2 redundant multiplexers for the national programs at that time with an external redundancy switch, and the ATI signal you see the dashed the dotted line is only in case if the ADI network fails. Yeah, so that they have at least the 10 national programs on air if something happens with the ADI network. Yeah, but the normal contribution is distribution is that they have the ADI signal. They transport that to all the ensemble multiplexer regions. Yeah, if you look here to region 1, for example, you see the multicast stream goes to the ensemble multiplexer region 1. And then we add here the 2 regional encoder programs into the system. Yeah, we multiplex both together, and then the output is 12 programs then via ADI and also via ATI if possible or necessary. And that happens for all 17 regions. And now here on the bottom, you see the region N+1 multiplexer. And this multiplexer collects all streams from all multiplexers in the network. Yeah, and if one system fails, then the N+1 multiplexer recognize what is missing here because we switch off then the ADI stream from the faulty multiplex if there's a problem, and then we load the right configuration. That's the reason why it's not seamless, because we can only react on that purpose if we know that one ADI stream is missing. And then this multiplexer replaces the 41. Yeah, that is how it works. Yeah, and as I said, we can also have a prioritization so that you can say that's the most important region, and then you can enter a value. Region 1 is the most important, get a 1, the next region get a 2, and so on, so that you have a prioritization for regions. Yeah, so if a higher prioritized region fails, then we switch to this region. Yeah, and the crisis announcement system was simply an additional encoder, which was installed then at the Polish authority. You can use it also for other bad things if you like. And they press simply a button and can do then a nationwide announcement. And now, of course, we discuss also the ASA standard with Polish radio guys. Yeah, so they're very interested to integrate that in the next time. And we will see. Yeah, good. Yeah, that's the case studies. Now the short advertisement block. Yeah, so that you see what we have on our products. We have different kind of encoders. We offer so for starting with 1 channel to 4 channels, up to 14 channels, yeah, in one box. Then we have here the different multiplexers, the small scale multiplexer, the professional DAMux Plus, the Fraunhofer multiplexer, of course, is also available in our portfolio. And the new one we will call Magic DAMux Multicore, which can run probably 20 multiplexes in one box. Yeah, or in one PC. That's a software solution. Yeah, that we will show then on IBC. Yeah, then we have monitoring and analyzing equipment. We are working very close together with Sven Mulka. He has nice systems for analyze and monitor systems. Yeah, you see they have now a new DAB RFX4. That's a quad transmitter as well receiver, so you can do a lot of stuff with these things. And in the middle, as I explained already, we have our monitoring decoder, which can handle up to 20 ADI inputs at the same time. Yeah, and for tunnel break-in systems, we have the Magic TBR. Good. Thank you very much. And now we have a coffee break.